Hello, everyone. My name is Taylor Wodzinski. Thank you for joining us today for Underslab, Vapor Retarders, and Barriers. Our presenters today are Roger Smith and Conley Bauer. But before I pass it over to them, just a quick few notes. Everyone will be muted for the duration of this presentation. If you have questions, please type your questions into the Q&A box and double check that you are addressing your questions to all panelists. We will be monitoring the Q&A and will be attempting to answer your questions in real time. However, if it requires a lengthier explanation or is a bit more complex, we may hold on to your question until the end of this presentation to answer anything verbally, or we can hold it to the after to get in touch with you afterwards. This is an AIA accredited presentation. Everyone will be receiving certificates sent to the email address you provided to us at registration. If you included your AIA number, we will also be submitting these credits directly to the AIA. With the holidays upon us, please expect a one-week delay in receiving certificates. And lastly, on the screen, you will see an email address, info@wrmeadows.com. If you would like a copy of this presentation or would like to get in touch with your local WR Meadows rep or have any additional questions for us in the future, please send us an email at info@wrmeadows.com and we will get you whatever you may need. At this point, I will turn over to Roger and Conley.
Thank you, Taylor. Appreciate that introduction and welcome everybody, and thank you for joining us today. As Taylor mentioned, my name is Roger Smith and I am the Architectural Service Representative for WR Meadows in Southern California. Joining me for today's presentation is Conley Bauer.
Hi, everybody.
Conley is the WR Meadows Architectural Service Representative for Texas and the surrounding southwestern states. As Taylor mentioned, our presentation today is Underslab Vapor Retarders, Below Slab Protection. Before we get started, one last reminder. Please direct any questions to the Q&A section and address all your questions to all panelists. Thank you again.
Before we jump into the true content of this presentation, a quick recap of who WR Meadows is, who we are, and why should you care about what we have to say. So we were established in 1926. WR Meadows is a family-owned company. It is still owned and operated by the Meadows family today. We have 12 facilities in North America. Most of them are in the United States, but we have a few in Canada as well. And we have a huge portfolio of products. We started off in 1926 with expansion joint materials. We still produce expansion joint materials today. We have since expanded our portfolio to include concrete restoration products, construction liquids, joint sealants, and decorative concrete. We have a lot of building envelope products, which is what we're discussing today, specifically vapor retarders, but we also have above grade air barriers and below grade waterproofing, both horizontal and vertical. The last note on this slide is just a shout out to Blue Ridge Building Products. They are a sister company of ours and they do soundproofing and insulation board. If you have any questions about soundproofing and insulation board, unfortunately, I'm not the correct person to talk to, but if you get in touch with us, we can get you in touch with the right person. Like Taylor said, this is an AIA accredited presentation. You will be receiving certificates, or we will be everyone will be receiving certificates. And if you supplied an AIA number, we'll be submitting those directly with AIA as well. What we're going to discuss today, some of our main learning objectives, is first to just identify the moisture movement that occurs in our structure, specifically below slab. Why do we care about uncontrolled moisture movement? What are some of the effects that we're trying to reduce? We'll talk about some industry standards, ASTM, ACI, and the different test methods we can use for those. And then towards the end of the presentation, we'll get more specific on product types and which product types to use depending on the site conditions that you have. We'll top it off with some of the best practices for design and installation methods and how to ensure that you get what you want on your project installed correctly.
So as we move into the science of moisture control and understanding that it is no longer adequate to just talk about underslab or no longer adequate to just talk about wall. We really are talking now about the building envelope or even further along the building enclosure. And it's important to understand that underslab, below grade and above grade systems have to work together, be continuous and compatible, because underslab is just one part of the envelope.
The best place to start is at the beginning. So in its most basic concept, the hydrologic cycle is this constant change of state from liquid water into water vapor or water as a gas. So we have water, liquid water that absorbs a lot of energy, typically through thermal energy, turns into a water vapor through evaporation. And then as that water vapor loses energy, it condenses back into liquid water. And this image on the screen shows the hydrologic cycle in a macro sense, where we have huge bodies of water that are evaporating and then turning into clouds and then condensing back through precipitation. But we also need to realize that this happens on a micro scale as well. It's happening around our buildings and even within our buildings, inside of our wall cavities. And this process of evaporation, condensation is constant. When we build a structure, we put our structure right in the middle of the cycle. So it's not how do we fight against this cycle, it's how do we work with this cycle to move moisture out of our buildings. And when we're talking about moisture protection, we're talking about moisture in three forms. The first being liquid water, which is the most obvious. Also water vapor, water as a gas, as it moves through air. And then thirdly, water vapor as it moves through diffusion. So that's water vapor moving through any other substrate other than air.
So in discussing these forms of moisture, we need to address how the moisture enters our structure. So let's start with liquid water. It's the most prevalent, probably, particularly when we're talking about below grade and underslab situations. And there's many ways that liquid water can enter our structure. One of them is to consider the water table. Is your building being built in the water table? Because if it is, you've got a whole different set of issues than if it's not. And it's important to understand where the water table is. In Southern California, water table can be as shallow as 5-6 feet and as deep as over 100 feet. So knowing the water table and knowing that if we have water in constant contact with our structure, we need to address that and the hydrostatic pressure that it places on our building. Another thing to consider for liquid water is site drainage. Is our structure in sandy soil and does it drain well? Is our structure in a clay-based soil or hard rock so the water has trouble moving throughout the below grade soil? You need to be able to address those issues and understand them. Another part of site drainage is to understand is if I've got that sandy soil and my building drains well, does that open the possibility for additional water from someplace else coming into my structure? So it's important to understand site drainage. Am I at the bottom of a hill? Am I at the top of a hill? Different issues can affect liquid water and drainage. And lastly, or not lastly really, but one of the other issues, and one of my favorites, is irrigation. You guys build beautiful structures and you landscape around them to make them aesthetically pleasing, look well, relaxing areas, greenscape areas. But this introduces water that we haven't considered in a soils report. So those issues have to be addressed. And irrigation and sprinkler systems can be a major source of water and water that we don't understand. This is something that we need to address because these can lead to unforeseen sources of liquid water.
Just because we have these unforeseen sources, as Roger is describing, doesn't mean that your project is doomed. Once we recognize that these are issues, then we're able to select the correct waterproofing material, how to design the correct system so that we do have enough drainage to accommodate this water. And the reason why these materials are so important is because we typically build our foundations out of concrete, and concrete is a fantastic construction material. It has a lot of advantages to it, but one of its disadvantages is it in itself is not very waterproof. So concrete is very porous and it tends to crack. It might crack, your concrete is going to crack. The questions there are, when is it going to crack? Where is it going to crack? How many cracks are we going to have? And how large are those cracks going to be? So if we anticipate that there will be these cracks in our foundation, then we're able to design a system to move that water away from the structure effectively. Lastly, for this slide is to talk about the waterproofing details. Sometimes that is something that is overlooked or not designed as well as it potentially should be. When we have bulk liquid water, any penetration through our material or our system is going to allow for another entrance of water into our site or into our structure. So making sure that we design these details well and that they are installed correctly is paramount for these systems to succeed.
So moving on in terms of water movement in the three forms, we want to look at air movement. And Conley, your discussion of details can't be emphasized enough, not only for liquid water, but for air movement and vapor movement in all of the building envelope areas. But air movement supplies a significant amount of moisture. Moisture-laden air moving through gaps and cracks can create real issues within the building envelope and within our building themselves. Types of air movement include wind effect. Obviously, wind blowing against our building will pressure air into the structure. A stack effect, a tall building that is being heated, hot air moves up. It would be impossible not to understand stack effect. And then also combustion, or I'm sorry, not to address stack effect. And then also the mechanical systems. Turn on your HVAC system, you create pressure differentials, air is going to try to move in and out. Not only do we have positive pressures, but we have negative pressures in stack effect. When air is moving out of the top of the building, it's being pulled in at lower levels. And while most air movement takes place above grade, and most of that is addressed above grade, it must be also considered that air movement takes place below grade.
That's exactly right. So typically the air moving above grade, but we don't have air in the same sense as above grade as we do below grade, but we have a lot of gases in our soil. So water vapor is one that we're very concerned about, but also there's other soil gases too that we should be addressing if they're present, like radon and methane. As like in that stack effect, warm air rises, positive pressure at the top, negative pressure at the bottom, that is sucking in these gases from the surrounding soil. And then our last category of moisture movement for our structures is water vapor moving from below slab. Water vapor moving through diffusion, like I said, is anything moving or any water vapor moving through a substrate other than air. So this is vapor diffusion. First, consider your soil. The soil acts as a giant sponge. It is completely saturated at 100% humidity at all time. And so no matter what your structure is being used for, it is probably not at 100% humidity on the interior, no matter what it's used for. So when we have this difference in humidity, we have a difference in vapor pressure. Vapor pressure is going to move from areas of high concentration to areas of low concentration, meaning that, oops, I got to pop up. Meaning that we're going to have this endless supply of moisture just feeding into your structure 100% of the time. Concrete is not a good vapor barrier on its own, so we need to put some other material there to block this vapor pressure, this constant vapor drive into our structures.
So let's take a look at the seasonal vapor pressures and drives that occur around our structures. Looking at this slide represents a warm summer day, probably somewhere in the southeast, Florida, Georgia, 90 degrees, 80% relative humidity, creates a very high vapor pressure on the outside of our structures. The constants are the pressure inside the building, where we maintain temperature, typically 70 degrees and 30% relative humidity that gives us a certain vapor pressure. And then understanding vapor pressure from the subgrade, underground and underneath our buildings, where it's generally accepted to be 55 degrees with a relative humidity about 100%. So you have these vapor pressures constantly exerting pressure on your structure, and Mother Nature is always going to work to even out these pressures. If you look at the same structure in the winter conditions, you see that they change outside, right? Now we're not in Florida anymore, right? 35 degrees, 20% relative humidity, and our vapor pressure is reduced considerably, but our pressure inside the structure, the same. Our pressure below the structure the same. So we still have those constant drives 365 days a year. So what does that mean? How can we kind of define this and understand what occurrences are taking place? So if we look at vapor pressure at 55 degrees, 100% relative humidity, you see 0.14 pounds per square inch. I know that's a small number in a small space, so we'll look at that a little bit further in a minute. If you look at conditioned space at 70 degrees and 30% relative humidity, we're looking at 0.108 pounds per square inch, or about half the amount. Now, if you take that and start to blow it up, you're down up to 15 pounds per square foot of pressure every day, 365 days a year, from below the ground onto our slab into our building. And what does that mean? Where does that take us? Well, it takes us to a significant amount of water when you start to break it down. You're looking at 10 gallons per day per 1,000 square feet of building. So if you got a 10,000 square foot structure, 100 gallons a day. For those of you on metric, that's 38.5 liters per 93 square meters per day. If you're looking at 50,000 square foot building, you're really starting to see a significant amount of water transferring from underneath the surface to above the surface. And you need to understand that that creates a problem of more issues than we normally see. The other part to understand, pardon me, is the vapor pressure differential can change based on what our structures are used for, right? If we're using something with a clean room, we might have a different need or vapor pressure differential than something like a parking structure. So what are the interior conditions, and what do you need to be concerned about in terms of vapor drive?
When we're looking at this water vapor transmission rate, ultimately we want to get it as low as possible. Ideally, we would get it down to 0. But we also know that we have all these materials that we can use. When we're doing that equation, we will be looking at the vapor retarder, but we'll know that you also have the other materials to help cut down on vapor transmission as well. So we'll have the vapor retarder, we'll have the concrete, we'll have any flooring adhesives, and then we'll have the flooring material itself. If you're up north, we're also going to have insulation to consider as well. So all of these different materials are going to help cut down on the amount of water that comes into your structure every day, which is hugely important. I feel like I don't have to spend too much time on this slab. Most people understand that there are serious consequences for moisture infiltration. And our first concern is always the health, safety, and welfare of our occupants. If we have uncontrolled moisture coming into our structure, it provides the opportunity for mold and mildew growth. If we have mold and mildew growth, our structure cannot work as intended. We cannot have a hospital, we cannot have a school, we cannot have an office building that has mold and mildew growth because it's not safe for those people to be in that occupied space. Same thing with odors and indoor air quality. Health is paramount, so we want to make sure that our air quality is the best that we possibly can get for our occupants. Secondly, once we've taken care of the health and safety of our occupants, we're going to look at the very expensive flooring that we just installed. That's kind of secondary, but it is still really important. It's expensive to build buildings, and many of these finishes can be very expensive to replace. So if we have uncontrolled moisture infiltration, there can be flooring adhesive failures, especially with the water-based adhesives. As far as the flooring material itself, often there can be distortion or delamination, and those materials would have to be replaced.
So why do flooring systems fail? Conley touched on the water-based adhesives, and being in Southern California, the land of the VOC, virtually all adhesives in our marketplace have become water-based and are subject to reemulsification if moisture is trapped underneath the flooring surface. But that's not the only reason that flooring systems fail. There's a little, and I kind of call it chemistry, in considering alkalinity of the concrete under the floor. When concrete is poured, it generally has a pH of about 12.5, or towards the alkaline nature. And as the moisture starts to leave and the concrete begins to cure, it moves down into a neutral place, generally speaking around 7.5, which is ideal. We want things to be neutral. We don't want acidity. We don't want alkalinity. And in this place, we're in a very good spot. Most flooring adhesives are designed these days to withstand a pH of 9 or below. So we're in a good place here. However, if vapor drive begins to come through our concrete and get trapped against the tile or the coating that's on the surface of our concrete, the alkalinity starts to rise again and will often exceed that 9.0 up into the 12 range again. And now we're in that area where our flooring adhesives are subject to fail. So you want to make sure that not only reemulsification, but that alkalinity can contribute to flooring failure.
Switching subjects a little bit, we're going to talk about the difference between a vapor barrier and a vapor retarder. And I have tried very hard this whole presentation to only use the term vapor retarder, but I know I have slipped up. It's very common to hear these out in the field used interchangeably, and at one time ASTM actually did recognize vapor barrier and vapor retarder as equivalent terms. But this is no longer true. ASTM now only uses the term vapor retarder, and there are very strict performance characteristics for what types of materials can be considered a vapor retarder, most notably the permeance rating of 0.1 perms or below.
And it's important, Conley, in looking at this to understand that construction materials are permeable. Now, yes, our retarders, and I use the term vapor barrier as well, and I'm sure I will, but our retarders have very low permeance ratings. But none of them, at least none of them that are used in conjunction with an underslab vapor retarder system, have a 0 perm rating. I'm not even sure what has a 0 perm rating. I suppose glass, I suppose maybe a sheet of aluminum, but I'd challenge you to put a sheet of glass underneath a concrete slab and pour concrete over it. So it's important to understand that all of these materials have some permeance, and there's going to be some amount of vapor going through the retarder. So in looking at vapor retarder characteristics, I just got done talking about permeance, and it is important to understand that permeance and low permeance are necessary to have a positive installation of a vapor retarder. But there's more to it.
Exactly. Permeance, excuse me, sometimes I have a hard time with that word. Permeance is important because we have to stop the vapor, but in this image, as you can so clearly see, there is a puncture. So we have other characteristics that we need to consider that will help or encourage the success or the failure of these systems. Puncture resistance being equal, if not more important, in my opinion, than the actual permeance rating. All of the ASTM standards, or all products under ASTM with that testing, is going to have a low permeance rating. So your success is going to come from the puncture resistance and some of the other characteristics. These materials are exposed to foot traffic and just general job site conditions. They take a lot of abuse before they're finally covered, and this unfortunately can lead to punctures. Even small holes in the membrane can allow a lot of water vapor through. So for example, there have been some studies done where an 1/8-inch diameter, like a nail hole, puncture in a 1,000-foot area of a membrane can change the permeance rating of that 1,000-foot area to a 0.93. And if you remember, the industry standard is 0.1 perms or less. So we're already above the recommended perm rating due to that 1/8-inch diameter hole. A 5/8-inch diameter hole brings that perm rating all the way up to 2.2, which is significantly larger than that 0.1 perm recommendation. So yes, vapor permeance is important, but really, really take a look at puncture resistance, because in this instance, we are able to see the puncture. We can patch the puncture before the perm, but these aren't, or excuse me, before the pour of concrete. My bad. But these aren't maintenance products. It's not something after the concrete is poured that we can go back and fix if we missed something. Hypothetically, if we have a really sharp gravel piece underneath this membrane. And it doesn't end up puncturing the membrane until the concrete pour. Well, that's not something we even know is there, and it's not something we can fix. It needs to be durable for the construction site, and it needs to be durable over the lifetime of the building as well. So these materials need to not be degradable. They don't need to degrade over time.
Yeah, exactly right. It's not very often that you're going to dig up a concrete slab, hopefully, to have to do maintenance on a vapor retarder system. Another couple things to consider is your job site. Is your barrier, I'm sorry, there it is, retarder compatible?
It's okay, Roger. We forgive you.
I told you it was coming. But is our retarder compatible with the surrounding soil, the surrounding environment? Are there things in the soil, whether it be methane or radon or possibly hydrocarbons left over, VOCs, I like to call them the enes, benzene, toluene, that could degrade our retarder over life? And then also, many of these systems will serve multiple purposes. I talked about methane and radon. Is the retarder I'm using capable of burying those things, or VOCs? You need to consider, when looking at the characteristics, what do you need from your vapor retarder system?
Jumping into codes and standards and different types of vapor retarders that we might see for different projects, ASTM categorizes them or separates the two different types of material with their own specific performance ratings, testing styles, completely separate. So the first is 1993, ASTM E1993, which is the bituminous vapor retarders. Now these can be more rigid, they can be more flexible. There's a variety of different products under this bituminous category, but these are going to be the more robust systems, significantly lower perm ratings, and usually, unfortunately, more expensive. More commonly, for slab-on-grade applications, we're going to see the plastic vapor retarders. So ASTM E1745 refers to the plastic vapor retarders. And within this category as well, there's many, many different styles of products. There's different thicknesses with 10 mil, 15 mil, 20 mil, 15 mil is the most common. We'll have extremely high puncture resistant products. We'll have the gas retarders, as Roger mentioned. So even though there's two different categories with their two different testing standards, there's a lot of variety within each of these categories. Now, the last one for ASTM, the 1643, is the standard practice for selecting, design, and installation and inspection of vapor retarders. And all that is best practices for making sure that the product you're selecting fits the site, that it's designed correctly, and that it is observed correctly prior to the concrete pour.
And American Concrete Institute, has also chimed into this. ACI 302.1R, ACI 302.2R, Guide for Concrete Floor and Slab Construction and Concrete Slabs that Receive Moisture-Sensitive Floors, address vapor retarders and permeants. But it's important to understand that ACI creates these documents for placement of the concrete in these situations. And you're looking at a document of 40 to 50 pages that has maybe a paragraph or two referencing permeants and the vapor retarders. It's also important to understand that ACI are not to be used in contract documents. There's a disclaimer on the front of these guides that says quite simply, these guides are not to be used in contract documents. Now, of course, you all know that your specifications are contract documents, so you don't want to use these in your specifications. So let's take a quick look at the two types of retarder systems defined by ASTM defined by ASTM, including E1993, as Conley mentioned, bituminous membrane water vapor retarders. If it's not bituminous, it doesn't meet E1993. That's quite simple. E1993 also establishes physical characteristics, including permeance and strength testing methods and requirements. And if you look at these requirements, they are quite stringent. You're looking at permeance of 0.002. That is extremely low. You're looking at tensile strengths that are extremely difficult to meet, and they provide excellent performance. A lot of the bituminous materials can be used in multiple application in terms of water and vapor. So if you're really concerned about the project, I know they're more expensive, but you might look at ASTM 1993 type products.
For the ASTM E1745 type products, the plastic vapor retarders, they also have a list of physical requirements, and they even break it down further into Class A, Class B, and Class C type products. You'll notice that all three of those have the same permeance rating. So they're all 0.1 perms. If they meet this standard, they're going to have at least 0.1 perm or below. You'll notice the difference in these classes are for tensile strength and puncture resistance. And as we've talked about before, punctures are a huge deal. If we have a puncture in our retarder, then the perm rating just skyrockets. So that's how we separate this good, better, best categorization, is not by permeance, but by tensile strength and puncture resistance. This image, or this has a couple photos of the puncture resistant testing. You'll see on the left, there's this long metal column. In the middle, we put the material at the bottom of that column, and then on the right, we drop that dart from various heights until the material is punctured. You will notice, however, in the right picture, that it is a rounded dart.
Yeah, and yes, it's a valid test, and it is used to test puncture resistance of these plastic vapor retarders. But this isn't real life. There are very few items on job sites that are rounded and smooth. So while ASTM gives you opportunity to look at comparison, it's also to consider real job light or job site realities. Never seen a piece of rebar that looks like this dart. So is it real life? No. Does it offer the opportunity to compare materials equally? Absolutely. So I want to turn again and talk a little bit about an age-old argument on vapor retarder placement. In particular, do we put sand above our vapor retarder, or do we pour directly onto the vapor retarder? This has been a long-standing argument, and if you look at ASTM E1643 back in 1998, there's a section that refers to a subsection to discuss the aggregate protection of a vapor retarder. ACI back in the 90s also addressed this situation. This is in 1996. Vapor barrier retarders required should be placed under a minimum of 4 inches trimmable, compactable granular film. Views have changed, and ACI revised their opinion a few years later to address these issues on a case-by-case basis, right? And that goes on today. Whatever your specification is, on the job site, we have arguments, and there are valid arguments on both sides of this issue. I'm not going to say one way or the other. It doesn't always apply. ACI currently recommends placing the concrete directly on the vapor retarder. WR Meadows is in agreement with this position, but you can have arguments on both sides. Arguments for a cushion or blotter layer include a place for water to escape, right? Bleed water to exit the freshly placed concrete, which can minimize slab curling, the sand can provide protection for the vapor bearing material on job site, construction damage, as I like to call it, construction durability. Arguments against, you can still have damage whether you have sand on top of your retarder or not. And you introduce moisture into this blotter layer, you've created a reservoir of moisture between your retarder and your slab. And once we start to see this vapor drive and differences in temperature and pressure and humidity, that moisture is going to come up through our slab and potentially cause the damages that we spoke about. All of these are valid arguments. Here's my position. Right. And I've been on job sites and I spent a fair amount of time working with contractors and distributors. So I've been in the hole and I've walked the job site. And when you look at a job site and your vapor retarder has been placed, often the general contractor will call the manufacturer. Hey, can you come out and look at this placement? We're getting ready to move on. We'd like you to take a look and let us know how it looks. Manufacturers will do that. I do it on a regular basis. And we'll come out and we'll look at the retarder. And if we see some punctures, as Conley noted earlier before, some maybe fish mouths in the tape, we'll get those fixed. And we'll write letters saying on December 17th, the observation of the vapor retarder installation at XYZ High School appears to have been installed according to manufacturer specifications. So at that point, you cover the retarder with sand, and the next guy on the job, that's right, the steel worker carrying his 3/4 by 20-foot rebar. Stuff's heavy, and those guys don't want to be on that job any longer than they have to. And as they're moving this material, one of them drops one of them. Invariably, it's going to happen. And this heavy piece of rebar pushes through the sand, punctures the vapor retarder. And the guy carrying it stops the job, literally holds up his hand and says, hey, I've got a problem here. I may have damaged the vapor retarder. Said no steel worker ever. What he's going to do is he's going to take that sand, he's going to smooth it over the hole, and he's going to go on his merry way. Now, Conley talked to you about what we've just done to our system, but nobody knows because it's covered. So the rebar's placed, all the details have been taken care of, and you call me back out to look at your job site. So I walk out on the job site, and my letter is basically going to read on, let's say it's now 12/24, it's Christmas Eve and I want to move on. No, I'm sorry, didn't mean to do that. But all I can address is, well, look, the sand looks marvelous because we don't know what has happened underneath the sand to the vapor retarder.
Looking at a few installation photos now. Roger, how many times actually has that happened to you where you're called out to inspect it after the sand has already been placed?
It's happened a few times there. It also happens even on waterproofing applications, Conley, where they ask you to look at a waterproofing application and the drainage board has been placed. So yeah, it doesn't happen a lot, but it happens, and not only with vapor retarders, but also waterproofing.
So a couple photos of the bituminous type of material, the installation. And like I said, there's more rigid, there's more flexible. This is a more rigid product. They taped all the seams. They used tape in this application. You can also use a liquid membrane for the seams as well. And you can see with the pipe penetrations, or I think those are pipes, they used a liquid membrane to seal around the base of the pipe as well. In this picture, a little bit more complicated because we have these pipe clusters. Ideally, we would like to detail each of these pipes individually. Unfortunately, you could not get a human hand in between those pipes to detail each pipe individually. So what we do with these clusters is we build a temporary dam around the entire cluster and we flood it with a liquid membrane. So it seals up all the potential gaps and cracks, and it flows through the pipes pretty well. It's known as a pitch pan application. So we're able to detail that area just by flooding it with a liquid membrane. This last picture is just another example of the install. This would be our ideal situation where we have no penetrations whatsoever, nothing to detail. It's just membrane, so there's not going to be any issues. But you can see that the metal has been placed and we are ready for the slab pour.
So a couple of photographs of E1745 installations, or plastic vapor retardant materials. And again, looking at this one, you can see the seams are taped. If you look in the background, you see some pipes that have been detailed with tape. There is some rebar present, or at least a mesh. Looks more like mesh to me for this installation. But basically a pretty typical installation. Moving ahead, and you see some things that are starting to get a little more complex. You know, whether they're grade beams that need to be addressed, and making sure that we get underneath all of the concrete. Here's a couple of Conley's favorite clusters showing up here. But you can see the installation, the materials is pretty relaxed. The taping seems to be done very well. Got a guy finishing up on that last cluster in the background. And then the next picture shows a situation where we really are ready to pour. Seams are taped, penetrations have been addressed, the rebar is up on some concrete stands, looks like we're ready to go. This would be the ideal time to get me back into the job to take a look at this, because all the work's been done. Yeah, it's a little bit hard to skip around the rebar, but this gives you the best opportunity to make sure that your job is ready to go. So let's continue our journey into systems by understanding what factors can influence the effectiveness of our systems. We've talked to some degree about material selection, right? We want to pick a product that works right for our job. Not every product works for every job, whether that's a 1993 bituminous or a 1745 plastic. Are we concerned about puncture? What are those sorts of things that we want to look at? Are we compatible? All those things are part of material selection. And then system design. We want to make sure we design a system that works within our project, but also within our location and with whatever other parts we're going to be in contact with. So system design, material selection are very important. There are other important factors that influence effectiveness as well.
The workmanship and the quality assurance is huge. So it doesn't matter which product that you've selected for your project. You selected the right material, you've done a great design, you've documented it clearly in your plans. But if you don't have an installer with high workmanship, and if we're not able to observe the installation and ensure that the installation was done correctly, then it doesn't matter how perfect your design is or how perfect your material selection is if it's not installed correct on the job. So have confidence that your installer has worked with this material before, have confidence in their team that they are going to raise their hand and say, we have an issue here if there's an issue. And then how well they work with their supplier and the manufacturer to make, exactly like Roger said, have someone come out, do a final observation before the slab is poured to clear up any potential issues before they're essentially lost forever. In selecting the material for your project, it's actually very simple. It's creating a list of site conditions that we're designing for. So is this a slab on grade project? Is there a below grade component? Is it an occupied space or a parking garage? Is there some sort of controlled environment on the interior? Do you have a high water table, poor drainage, soil gases? If we're able to identify all of the site conditions that are challenges for us, then it is very simple to just connect those site conditions to the product that's going to address those site conditions.
Another thing to consider is what's going into my structure. Is there sensitive floor coverings, right? Am I using an epoxy floor, or am I not covering the concrete at all? Or if you start to think about like a gymnasium, high school or college gymnasium, or a hardwood floor, those flooring systems are very, very sensitive to moisture and also considerably expensive to replace. So you have to look at all of these issues within the floor system, as well as the systems around. And then compatibility, I mentioned it before. Can I transition to my other systems, whether I am at slab on grade, or do I need to transition to a waterproofing membrane? Are my systems that I've selected for my vapor retarder compatible with my surrounding systems?
When we get into specification, you've done all this work in selecting the right product, the right system. How do we ensure that you're actually getting what you want on your building? So first thing you need to identify is your material type. Are you using bituminous? Are you using plastic? And then after you identify the material type, you need to identify the level of performance. What are the performance-based characteristics that you're requiring for this project? Once you have material type and level of performance, then you're going to get the correct range of products that is priced out, that is bid. But those are the two main things you have to include to get the right product. I very rarely see proprietary specs for Underslab. There's usually a basis of design or a list of multiple manufacturers listed. If possible, instead of doing a basis of design or equal, I encourage you to do the research and list out the exact product name for each manufacturer that you're approving. And the reason why is to ensure that the equivalents that your contractors are submitting are actually equivalent in the areas that you care about. Verify which test was used for these different products to achieve those performance values. Ensure that the products you're putting in your specification are apples to apples, meaning the same material type, same level of performance. Unfortunately, I see this often where within one specification, they'll list a 15 mil plastic vapor retarder right next to a bituminous vapor retarder. And as we discussed, these two types of materials have vastly different levels of performance, vastly different price tags, vastly different details, and other physical characteristics. And if you're presenting these two options to your installer, to your contractor, a 15 mil plastic or a more robust bituminous, then the only product they're going to consider is the less expensive one. And maybe that is what you want, maybe that was what you intended, but it could not be. And it's not a true competitive spec because those products aren't true equals.
Yeah, and that can be so confusing within a specification. I touched a little bit on compatibility with surrounding systems in the previous slide, and I'm going to hit it again because one of the things we've seen is over the past years is the desire to have single source systems. So a manufacturer that can provide under slab, below grade, above grade air barrier systems, or the entire building envelope. I talked about the building envelope at the beginning, and creating these single source systems gives the owner and the general contractor some sort of comfort as to knowing these systems are going to transition easily. If there's an issue, you've only got one person to call to handle details or something that may have happened. So single source systems might be one way of looking at it. If you're not concerned with single source, just make sure that your systems transition well between one another. And most underslabs do transition quite easily, but not always. Also considering substitutions, right? You all get the VE, right? You all get the RFI. It's also important to consider these things in that situation, right? Not all products are interchangeable. Not every product works for your project. So you've taken the time to select these systems. Make sure that if somebody's coming to you with a request for change or a VE, that product fits into your project. Because if it doesn't, your value engineered product is going to run out of value very shortly in terms of new transitions, new details, delay in work, all of those situations that can come up. So just a quick review. We've looked at installations before. I really love this slide because it does show the ABCs of a 1745 installation. You can see the material is being stretched out and laid out in the top left-hand slide. Interesting point about this project, I believe it was up in Northern California, is that there was some relatively high winds during the installation. And rather than have the material blow away or continually being rolled up, you can see they used sandbags to hold it in place while they were laying it out. The center picture, taping of the seams. And again, using this picture because I love the way these guys are doing the work. The tape is being held taut by the gentleman on the left while the other gentleman is adhering it into the system. This is going to ensure that we get a good, solid adhesion to the seam, and we limit fish mouths, right? If fish mouths are just as dangerous as punctures in terms of allowing extra vapor to penetrate. And then at the bottom, again, almost ready to go. We've got that multiple penetration system that in this case was taped around. One of the more difficult details to address, can create many problems, but stresses the idea that detailing is key to the building envelope installation. So here's a specific detail. This detail addresses penetrations. And the CAD detail on the left is very simple, right? It's retarder and some tape, addresses the penetration, and then the concrete is poured on top of it. And while that's relatively straightforward, if you look at the illustration to the right, you get a much better look at an actual single pipe detail. And they're fairly intricate, and there's a fair amount of work that goes into getting that tape into the right position, making sure it's sealed around the penetration and sealed to the barrier. Well, if you take that detail and then look at a cluster that we looked at in the bottom right hand, maybe this is the detail you're looking for. And while the CAD detail on the top left is relatively simple, shows the retarder and the membrane flooding around the multiple layers, the three-dimensional isometric detail on the bottom right gives you a much better look at how that is done, right? So we're built a dam around the cluster, and we're filling that area with a liquid membrane that's going to seal around all those individual pipes.
Looking at a few of the transition details, going back to that idea that this needs to be entire building envelope protection. So we are going to be tying into other systems as well. This detail here is for an elevator pit connection. We have a vertical waterproofing, and that concrete that will be poured first. And then we have the vapor retarder, the plastic vapor retarder, overlapping with a liquid membrane, creating that perfect seam, that continuous protection from the vertical to the horizontal. In this, we have a slightly different situation where we have the slab turning up to additional waterproofing. So we have the vapor retarder underneath. It'll turn up the edge of the slab. The red line in the lower right is just an additional detail membrane. It's extra protection on those inside and outside corners. And then the waterproofing that goes vertical. In the upper left, you can see there's a little round circle at the bottom of the waterproofing that laps on top, and that's just to create another better seal at all of those transitions. We get this question a lot. I'm asked this probably at least once every 2 weeks of, do we wrap the footings or do we not wrap the footings? And from someone who is in the moisture mitigation business, we would prefer to wrap the footings from the standpoint of moisture control. Unfortunately, this does not always happen because moisture control is not the only thing we need to consider when we're building a building.
Yeah, you're absolutely right, Conley. And it reminds me of a time when I was relatively new with WR Meadows. Actually, I think it was my first observation of a vapor retarder installation. And so, you know, hard hat in hand, I'm out there thinking I'm really going to take care of this, and they were not wrapping the footings at that job, and I made the comment that it would be a much better system if we could wrap the footings, and you know, tried to press my point pretty hard with the GC, who was then more than delighted to refer me to the structural engineer, who had insisted that his footing be in direct contact with the earth, something we find here in Southern California. As you know, we have fair amount of seismic activity. And this structural engineer had no interest in having a piece of plastic between his footing and the soil. So the young pup went back with his hat in his hand, understanding that while you might have a very good argument, you may not be able to fight City Hall in the terms of a structural engineer.
Yes, always do what your engineer says.
Yeah, exactly right. Exactly right.
And just to wrap it up, I mean, we talked about a lot of different things today. Overall, of just how moisture is moving into our structures, about the constant vapor drive and why we need to protect our structures against it. We talked about some of the ASTM standards. Separating those two different types of vapor materials is very important, and understanding which one you need for your structure, and specifying and designing and installing it the correct way, and hitting home that idea that details are critical. That's other than the puncture resistance aspect of it, details are probably the most important for the success or fail of your system. So getting those right and installing them correctly is the most important thing.
So this concludes the AIA portion of this presentation. I hope you found it informative. Before we move on, and hopefully we've got some questions we can address in our remaining time, I wanted to take a minute to talk about WR Meadows' website, www.wrmeadows.com. We have a plethora of information, and yeah, we've got data sheets and we've got SDS sheets, But we also have an extensive source of CAD details available. We have BIM modeling. We also have guide specifications. We've got project profiles. We've got training sites. There really is just a whole bunch of information available there. I encourage you to visit and check it out. And then just a real quick shout out, as Taylor mentioned, info@wrmeadows.com. If you're looking for a copy of this presentation, that will be available. Give us an email, give us your information, we'll get it to you. If you're looking to have somebody maybe come out and do a private presentation for your firm, let us know. We'll get back to you. If you just want contact with somebody to give you a call to follow up, shoot us an email, info@wrmeadows.com. We'll get back to you with the information that you desire. So thanks so much, everybody. Conley, thank you so much. Wonderful job today. Let's see, Taylor, what's it looking like for questions?
Thank you, Conley and Roger. Excellent job, guys. I do just want to mention real quick that this presentation will be available on YouTube as well. We did receive quite a few questions during our presentation, and it looks like they were addressed during that time, but let me double check to see if any has flooded in at this moment. Okay. So one did just come through. It says, I have seen the use of vapor retarders affect the performance of the contraction joints in slabs placed directly on concrete. The surface is smoother than aggregate and the friction is decreased. Some joints fail to work and larger movements are seen on the few joints to work, and larger movements are seen on the few joints that do work. And then nothing else has come through. That was more of just a statement than a question.
Yeah, that's an interesting point, and not to dismiss it. That yes, you probably do have a little bit less coefficient of friction if you pour your concrete directly onto the vapor retarder, particularly plastic vapor retarder, like a 1745. I've never really come up to that. I'd love to find out who gave us that question so that we can reach out to them and address it. It goes back to my point. There's intelligent and valid arguments on either side of that sand issue, and that discussion goes on all the time. So yeah, it's a very interesting point. It's not been brought to my attention previously, but would love to reach out at some point and discuss that.
He did mention that better jointing deeper or sooner may be required as well to that statement. And there's no other further questions at this time. We ended up addressing all of them. So if I don't see anything soon.
Well, we're just about at the top of the hour.
Yeah.
So I thank you again for your attendance. Those of you who have been attending our series on this fall, I hope that you've learned something from it. I hope we've provided you some information. If you're looking for more information, please reach out. We'll get in touch with you. This concludes our series for the fall. Moving forward into 2021, I'm sure we're all looking forward to that. We will be looking at doing presentations on a regular basis, and hopefully you all have a great holiday, and we come into 2021 re-energized with a great new outlook on life. So thank you, everybody. Much appreciated. Conley, thanks for your help. Wonderful job, and everybody have a wonderful rest of the week.
Excellent. Thank you, Roger.